Hello, my name's Danelle Hogan, and today we're going to be talking about binary mic drop math and how to turn your students into human computers. And let's jump right into it and get started because we only have 30 minutes. Today we're going to talk about 4 lessons. I know in 30 minutes, 4 lessons is pretty quick, but we'll go faster than you normally would with students, obviously. And then there are lesson plans for each of these different lessons so that you can go back and slow down and read through them again. But we're going to talk about patterns and then binary mic drop math cards, parity and error detection using cards cut out of cereal boxes or something like that, and how to turn your students into human computers that can send secret messages. So let's get started. The first patterns activity uses cards that you can either print out like these, or you can also do this virtually very easily. I've done both. So on this card, you would have students look for patterns that they notice. And on this card, you can see a variety of different patterns. First of all, they'll notice that it's only odd numbers. They'll notice that it is +2 every single time. They'll also notice that it goes up by 8 as you go down the columns. As you go diagonally, it goes up by 10. Obviously, this will take them some time to figure out. As you go this way, it goes up by 6 each time. And then we'll have them look at the next card and look for patterns again. What do they notice? They might notice it goes +1, then +2, then +1, then +2 on this card. They might notice that along this diagonal, again, it goes up by 9. And along the other diagonal, it goes +7, and then +5, and then +7. So that's interesting. And they might notice that the second and the fourth column are actually the same. And at this point, what we would ask them to do is ask them to predict which number they think the next card might start with. And the most common answer, of course, is 3. And we wouldn't spend too much time making a prediction about this next card. And so they'll probably guess 1, 2, 3 obviously comes next. And so then when you show them the next card, it's not a 3, it's a 4. And so then we have them look for patterns again. And what they might notice is it goes 4 numbers in a row, and then it skips some, and then it goes 4 numbers in a row. So it's +1. These are all consecutive on the second row. And then they might notice that the last column is still the same. They might also notice that it goes up by 9 across the diagonal again. That still holds. And on. So it goes +9, +9, +9. And then across the other diagonal, it goes +7, +7, +7. And so you would have them notice more numbers. And then at this point, we're going to have them now guess what they think would be on the next card. And we're going to take a little bit more time here. So as we take more time here, we want them to think about making more than one prediction. So a big misconception in science and mathematics is that you would only make one prediction, one hypothesis, and then see if it's correct or if it isn't correct. Is it supported by the evidence or is it not? That is a big misconception. We would prefer for students to try to find as many different patterns as they can, to make as many different predictions as they can, again, supported by mathematical patterns that they can put together. So in this case, they might think that it's going to be a 6 because it goes 1, 2, 4, 6. Of course, that pattern doesn't hold for the first card, but sometimes the initial part of the pattern is a little bit different. You can also see that it goes, in terms of jumping, it goes +1 from 1 to 2, +2 from 2 to 4. So maybe it's 4 + 3, and it could be a 7. So it could be +1, +2, +3. Or maybe it's going to be an 8 because you double 1 to get 2, you double 2 to get 4. If you doubled 4, then the next one could be 8. They have also seen patterns that support the number 9. So you're going to have them make a bunch of predictions, and then you're going to show them, actually it is an 8, and then make a prediction about what the next card would be, look at patterns again. And then they will see that the next card starts with 16, which doubles. And so the pattern clearly at this point is how it doubles each time, the number that the cards are starting with. And this is also a good lesson in why we need to collect more data in science instead of just a few data points. With just these first 2 or 3 cards, we can't really tell what the pattern is. But by the time we have 5 cards, it'd be really difficult to come up with a pattern that would predict anything other than 32 on the next card, which is in fact what it would be if we had a 6th card. The other cool thing that you can do with these cards is you can actually figure out the number that somebody is born, the day that they were born. So I would say to students, okay, now think of the number for just the day that you were born, not the month and the year, just the number for the day. And they would then tell me yes or no, is your number on the first card, the second card, third, fourth, fifth. So 5 yeses or nos, and I would be able to figure out their birthday pretty quickly. And when I've done this virtually, I've had people just put 5 yeses or nos in the chat, and then I can call their name out and tell them what their birthday is. So how the heck does it work, and how is it connected to binary numbers? Let's find out. So if we were to look at somebody's birthday, let's say your birthday is the 10th, so you were born the 10th day of the month, then you would have said no, yes, no, yes, no. And I would be able to tell immediately that your birthday was on the 10th. I would say, oh, it's on the 10th. And you would think, wow, how can she do that? So let's look at how it actually works with a different example. So let's say that the number is 15. So then you would say yes, 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 no, because 15 shows up on every single one of those cards. And how do I figure out what your birthday is? Well, on all the yes cards, I just add up the top left number on each card that you said yes to. And wouldn't you know it, 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. Let's go back to the last card and see if that works as well. So for 10, I would have added 8 plus 2. Sure enough, that's 10. And if I'm sly and practiced enough, I can make this look like it's magic, although there's no such thing as magic, only math and science, which does not make the world less awesome, just more interesting to try to figure out how things work. And so again, that's how you're able to do this mic drop math trick with these cards that you can either print out from our website or you could do it here. So let's think about what is my favorite number and see if you can figure it out. So if I was saying yes and no for my favorite number, I would say, yes, it's on the first card. No, it's not on the second card. Yes, it's on the third. Yes, it's on the fourth. And no, it's not on the fifth card. So based on what we just talked about, can you figure out what my favorite number is? And again, you just have to add up the top left numbers on the yes card. And if you did that mathematics correctly, you should have gotten that my favorite number is indeed the number 13. And so if you are doing birthdays, obviously you can only do the trick once. Once you've picked somebody's birthday and figured it out, they can honestly just pick any number between 1 and 31. It just turns out to be very convenient that that range of numbers allows you to use somebody's birthday as the number that you are guessing, which is great. So again, this is what we saw here with the yeses or nos. And you might think, but what if I have really young students, like students that can't yet do addition or can't do addition in their head, or they don't want to write it out on a piece of paper? No problem. We have a solution for kids that are very young. So for kids that are very young, 3, 4, 5 years old, as long as they can count up to 31, then you can print out these cards so that on the back, they have dots on them that correspond to the numbers that are in the top left corner. And so in this case, if I had said yes, no, yes, yes, no, the child would take those cards that I said yes to, put them in a pile or flip them over, and then they would count up the dots on the back of these cards. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11, 12, 13. Aha, your number must be 13. So even small children can actually learn the algorithm for doing this trick and how it works. And it turns out again that the way that it works related to binary is because when you're saying yes or no to those cards, you're actually telling me 0 or 1 for the first 5 places in binary. And with 5 yeses or nos, or 5 zeros and ones, I can represent 32 different values, 0 being one of them that isn't very interesting, that would just be no, 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 no. And so that's how I'm able to figure this out and how it's related to binary. And there are some great videos that explain a bit more about binary in this lesson, which you should check out. One thing that some students and teachers asked us as we were doing this lesson is, well, but where did the numbers come from on the cards? Like, how did you figure out what numbers were on the cards? So you can, if you have time, do a lesson where students actually build their own cards. And we have templates for them to build their own cards with 0 through 31, Or we have 6 cards that go through 1 through 63 or 1 through 127 if they want to build cards that go all the way up to 127. But in this basic setup, what students would do is they would have blank cards and these numbers for the first 5 places in binary in either 0 or 1. And then they just iterate through turning on cards when you need them to be on to represent a value. So this would be what the situation would be for representing a value of 1. And so you put the number 1 on that blank card. This would be 2. And so 1 goes down and the next card goes up. So 2 only goes on that card. To represent 3, we'd have to turn on the numbers for both the 1's place and the 2's place in binary. And so 3 goes on both of those cards. And you keep iterating through 4, 5, 6, 7 goes on 3 different cards. And you just keep going until you fill out the cards completely, all the way to 31 or 63 if you're doing 63 and so on. And you can see how 10 goes on this card and it has to start filling up the second row of that card that's in the 2's place. And so that's how you can build your own binary number cards to build better understanding of how that system is working and how we're using just 0s and 1s in order to represent whatever number we want to, depending on how many places we add in. All right, so now let's talk about turning your students into human computers. And for this activity, students would need to cut out from either a cereal box or from something that has printing on one side and then cardboard colored on the other side. So they're just cutting out 36 of these cardboard pieces from something that is like a cereal box or something. If you have younger students, you can also print out these bit cards, which are just 0s and 1s on one side. So 0 on one side and 1 on the other side from our website. These are a little bit more concrete. Otherwise, on these cards, we're using the cardboard side to represent a 0 and the printed side to represent a 1. Either way it works out. It's kind of cool though, and STEM on the cheapie that you can do, use just cereal box, cards cut out of a cereal box to do this lesson. So this lesson initially comes from CS Unplugged, the parody part of this lesson, the first part, and then we've added in the part where you can actually code a secret message and then decode it later. And so the first thing you would do is have students lay out their cards in a 5x5 grid. And they can just do this randomly at first, and then we'll talk about how they would code a lesson. So they would just put out a 5x5 grid. You can also print out this grid from our website just to keep things a little bit more organized, but you don't honestly have to have this or even the letters and numbers, but it makes it nicer for guessing where errors are later on. Then what we need to do is we need to put on the parity bits that go along with this data. So when computers are sending information back and forth in 0s and 1s, they put parity bits around the outside. They add a little bit of additional information so that when the other computer receives the message, it can check it for errors. So to add those parity bits, what you have to do is look at the top column A, and we need both the printed side and the cardboard side to be even numbers of those particular settings. So in this case, we have 2 cardboard sides that are facing up and 3 printed sides. 3 is an odd number, so I need this card here on the next card on row A to be printed side up. So now we have 2 that are printed and 4 that are printed and 2 that are cardboard. On the next row B, we have 2 that are printed and 3 that are cardboard. So in order to make 2 even numbers, what we need is a cardboard side up. And so we'll put that one cardboard side up. So now in row B, we have 2 that are printed and 4 that are cardboard. In the next row, we have 3 cardboard and 2 that are printed. So the odd number is the 3 cardboard. So this has to be cardboard in order for it to become an even number. So we're going to put that one cardboard side up. The next one, we're going to go a little bit faster here, would be print side up. So it's 2 and 4. The next one would be print side up so that it's 4 and 2. And then we're going to work on the columns. And so for column 1, we have 2 printed and 3 cardboard. So that one has to be cardboard. The next one needs to be printed. The next one needs to be printed. The next one needs to be printed. The next one needs to be cardboard to make it even. So you only have one cardboard, so we need that to be even. So we're going to add another one to make that 2. And then if you've done everything correctly, then this piece right here should complete both the row and the column to make it even. So the row, I would need it to be printed. The column, I would need it to be printed to make it 2 and 4. And so sure enough, we'll add a 2 there. So now every single row and every single column has an even number of cardboard side up and printed side up. So if information was to get messed up when you're sending it from one place to another, then you would be able to detect that error if you were the computer receiving the message. And here's how it works. That grid that we just had, I secretly switched one of the cards. I flipped one of them over, and now we're going to figure out how the heck to detect the error that I created in this message. So one of these cards is not where it belongs. Something happened here. And so we're going to figure it out which one it is by first looking at the rows and looking. The first row A is still even, 2 and 4. Row B is still even, 2 and 4. Row C is still even, 4 that are cardboard side and 2 that are printed. Row D, 3 cardboard and 3 printed. That is odd. And so row D definitely has the error in it because it has odd numbers of printed side up and cardboard side up. Now we're going to look at the columns and see which column has the error in it. So when we look at column 1, it has 4 and 2. When we look at column 2, it has a problem. It has 3 and 3. So the error must be in column 2. And if we then follow that row and column to where they meet, sure enough, the card that I flipped over was D2. And if we toggle back and forth between this picture and the original picture, you'll see that sure enough, this is the original. And then here's the one that I had flipped over. And then back to the original message. And this is the one that has the error in it that we were able to detect. And so that is where the CS Unplugged lesson kind of left off, just with error detection and what they call parity bits. But we took it a bit further and actually coded a message in these cards. And when we coded that message in these cards, we're using a number of different things, including the ASCII, American Standard Code for Information Interchange. So ASCII is pretty common in terms of how we represent letters and numbers and send those messages from one place to another. So if we look at our grid here, we're going to ignore column 6 and row F because those are, again, the parity bits. The information that we were sending from one place to another is really in rows A through E and columns 1 through 5. And so we're going to look at this row by row and we're going to decode it using this system here. And as I said before, if it's cardboard side up, that represents a 0. If it's print side up, it represents a 1. So this first row would be 1, 0, 0, 1, 1. Can we figure out which letter that is? And we're going to go row by row and figure out this word. So if you have younger students, representing abstractly zeros and ones with cardboard pieces like this might be difficult. So again, you can also print out from our site the cards where you can put zeros and ones on here, so it makes it a little bit more concrete. And they could use these instead of the cardboard, cut out cardboard pieces. But if you're doing this from a distance, they might have access to the cardboard pieces and not a printer where they can print out these bit cards. So when you're looking at this and decoding it, I'm going to give you just a couple minutes to figure it out. So you're matching up the row A, 1, 0, 0, 1, 1 to the letter that it corresponds to from the ASCII, American Standard Code for Information Interchange. And so that first one is S. The second row is T. The third row is E. Row D is it A. And the final row is, of course, M. And so I have encoded in this with these cards, the word steam using these cards. If you knew the rules, how to decode this, then you could figure out that it would decode and write the word steam. And again, if I have enough zeros and ones, then I can send all kinds of information from one computer to another. Let's do another one. Here's the next one. And so this is a different word here. Can you decode it? And I'm not going to give you the zeros and ones this time on top of it. So the first row is 0, 1, 0, 0, 0. And so on and so forth. And I'm not going to tell you what the answer is. You can pause if you need a little bit more time to figure it out, but I will give you a hint that it is in fact an animal. If you want to be able to represent words that use uppercase and lowercase letters, then you'd have to use 7 bits. And so then students would have to have a 7x7 grid with the parity bits. Then they would be adding on another row and column. So they can do that. There are directions for how to use the 7-bit ASCII system so that students can actually put punctuation on their messages and so on and so forth. But they would have to string a bunch of these rows together in order to send that information. Hopefully you've decoded that word and figured out what it was. And again, this lesson, along with all of the templates and the ASCII coder on our website. The other thing that you can do with these, you can also introduce students to ASCII art. So it turns out a long time ago, and depending on how old you are, you may or may not remember this. When we were sending messages back and forth, email messages, we would actually also send sometimes a picture, but the picture was created using characters from the ASCII codes to create them. So using parentheses and brackets and all of this stuff, you would create an image that took a lot of space, so maybe a cat or a dog or something like that, and then that's how you would send it out. So also in this lesson, it details how to bring that art piece back in using ASCII art. There's even ASCII animations, so showing a little person that is moving with a series of different little images that you create using just characters that look like something. So it's an interesting it's an interesting look at how we used to send these silly pictures back and forth using email when it first came out, and also a fun challenge for students to try to represent something and have other students guess what it is using ASCII art. And there's some great links that'll show you where you can find some other examples, and even your students can load them up. If you're nerdy like me, you also have t-shirts that are nerdy. And so this is a robot joke that you have to decode using the ASCII system. On my t-shirt, it has the 8-bit code for the letters. And so in this case, to decode it, just ignore the first 3 numbers in each of those and decode the last 5 numbers, which match to the alphabet from the ASCII system. And you can figure out what this joke is here. One thing that is interesting is, binary numbers. People generally think that they're relatively new, that we only invented the binary number system because we needed computers to talk to each other. So another great lesson that we have in this collection, which you can find on our website, is a lesson that looks at how Russians and also ancient Egyptians were multiplying numbers together. And it uses a system that is connected to binary. So 4,000 years ago in ancient Egypt, they were using binary numbers in combination with decimal 10 numbers base 10 numbers in order to multiply 2 numbers together in a way that they thought was simpler than any other way that they had tried. So that is pretty cool to look at some of the history of mathematics and how that ties to binary, and also demonstrate to students that binary numbers are not, in fact, something that were just created for computers to be able to talk back and forth, but we've had this idea of different base systems and how they work for thousands and thousands of years. It's not something that was just invented for computers. And I do think that's critically important to share with your students. Thank you so much for joining me today for this look at some mic drop math and some how to turn your students into human computers. All of these lessons really can be done virtually. I've done them with students as young as about 6 years old, all the way up to adults. They're really engaging. If you print out the cards, it's a fun thing to do for math nights and other things like that. And like I said, we have 1 through 31, which is 5 cards that you print out, and you can either put the dots on the back or not, depending on if you're going to be using them with younger students. The cards that are 1 through 63 also have a version where you can print the back side. If students don't need the dots on the back, then you don't have to print that second side. And then we have 1 through 127. And then even for the youngest kids, they might start with 1 through 15. And also on our website, we have 1 through 7. So if they're not yet counting past 10, even our youngest students can start to engage with binary numbers, which I think is really incredible and important to get them loving math and seeing how it's everywhere, and building their confidence that they can do, everybody can do math. That's critically important as well. Thank you again for joining us. If you want to find the other lessons, you can go to our website or directly to that bit.ly link, which will take you to the collection of lessons we have about binary numbers and turning your students into human computers. Thank you.